everyone. I am Akshaya. Today I am here to present my project Gen AI based surgery multi-model surgical scene understanding system. This project aims to build an AI powered assistant that can understand what's happening during a robotic or a laparoscopic surgery in real time with full context. Our goal is to make surgery smarter, safer and more efficient using artificial intelligence. Coming to the project overview, robotic surgeries are very precise, but they lack cognitive intelligence. They don't really understand what's going on in the surgical scene. Most existing AI models handle one task like tool detection or face recognition, but they doesn't do together. Our project bridges this gap by combining multi-vision based tasks under one unified AI model. This research behind our project is inspired by the paper Pixel-wise recognition for holistic surgical scene understanding, which introduces the TAPIS architecture and the GRASP dataset. Coming to the system architecture, this is the complete architecture of our system. It consists of four main parts: front end, back end, model APIs, and the database. For the front end, we have used the React where user uploads the surgical video or the images and log in using secure authentication. Coming to the back end, we use the Flask API, acts as the controller that connects all the AI models. Model APIs handle specific AI tasks such as detecting the instrument, segmenting the instrument, face step recognition, and atomic actions. And the database. For the database, we have used the MongoDB where it stores the user details, uploaded data, and the generated results. The data flow starts from the user upload, goes through the model inference, then returns to the result visualization, and finally saves it into the MongoDB. Coming to our research paper summary, our paper is built on the GRASP dataset and the TAPIS architecture. The GRASP dataset is the first public dataset for the holistic surgical scene understanding. It includes 13 robotic assisted prostatectomy surgeries over 32 hours of video with annotations for 11 phases, 21 steps, and 7 instruments and 14 atomic actions. The TAPIS architecture is a transformer based model that performs multiple tasks: long term tasks like face and step recognition, short term tasks like instrument segmentation and action detection. It combines features from mass to former and MVIT to achieve context aware, pixel level understanding for surgeries. The results showed off. Coming to the TAPIS architecture, this TAPIS architecture connects several modules for multi-level understanding. Master former processor achieves each video frame to segment instruments at pixel level. MVIT extracts spatial and temporal features from short-term video clips. Classification heads predict the surgical phase or step based on these features. Action heads predict which instruments are involved and what actions are being performed. This allows the system to understand both what is happening and why is happening, just like how human understands. The project architecture. Our own architecture adapts the TAPIS concept into real-time web system. The backend connects four AI models that together provides holistic scene understanding. Each handles a specific level. MVIT for video-based feature extraction, Master Former for instrument segmentation, TAPIS Transformer for phase and step recognition, MVIT for atomic action detection. The combined output gives a complete view of the surgical process. Coming to the approach in the paper versus our approach. The paper approach called TAPIS mainly focused on the research and the benchmarking part. It performed four tasks: face detection, step recognition, instrument detection, and atomic recognition, but only in an experimental setup. Our project Gen AI Surgery goes beyond that. We focused on real-time implementation by connecting multiple transformer models like MVIT, Master Former, and TAPIS into a single AI pipeline. Unlike the paper, our approach also includes a front-end and a back-end system. The React Web interface allows users to upload the surgical video. The Flask-based processes them through the models, and MongoDB stores the results and the history. Coming to the self-attention mechanism. All our transformer models are based on the self-attention mechanism. In simple terms, it helps the model learn which part of an image or video are related to each other. The formula is clearly visible here. Attention of q, k, v equals to softmax of q k to the power t by under root of dk whole v. Here, Q, K, and V stands for query, key, and value matrices. This lets the AI understand relationship between image, patches, or video frames, giving it global context awareness, which is very important for surgical videos. Coming to the model foundation, MVIT. The MVIT is used for tasks like instrument detection, action recognition, face and step recognition. It captures both fine detail and overall motion, which is important in understanding several surgical procedures. Because it works for both short clips and the long videos, it acts as a unified backbone for all the tasks, improving efficiency and consistency. Coming to the master former is used for pixel level instrument segmentation. It clearly separates one surgical tool from another in the same image. Its architecture has three parts: a CNN or a transformer encoder that extracts the features from frames, a pixel decoder that refines the features, a transformer decoder that predicts class labels and binary masks. The final output highlights tools like scissors, needle drivers, or the forceps on the surgical frame, showing clean boundaries. The training and the training accuracy. We trained our models on annotated data from the GRASP dataset. The training followed strict parameters to ensure high accuracy. We have used the optimizers like Adam. The loss function is the binary cross entropy with the logits for multiple label outputs. We have run up to 100 epochs with the early stopping to prevent the overfitting. Here you can see the images for the training epochs, instrument detection, image segmentation, and atomic actions. For the long-term task, that is phase and step detection, we have run the up to 518 epochs. In conclusion, we developed a complete Gen AI based multi-model surgical understanding system. It integrates four transformer based models into one intelligent pipeline that can analyze the full surgical scene. Real world use includes AI assisted robotic surgeries, training and skill evolution for surgeries, post operative analytics, and workflow automation. This project shows how AI can support doctors in making surgeries safer and more reliable. Now let's look into the live demo of our project. This is the home page. This is how our AI works. These are the benefits of our website. This is the get in touch page where user can send their feedback so that we can review them. And let's get started. This is the login page. So if the user is logging in for the first time, he need to create his account, or else he can use the sign in with Google option. There is another option as well. User can even log in with his OTP. Let's check it that also. Yes, the OTP has been sent. Yes, the login successful. So in this way, you can log in through any means. So and you can see the history of the previous uploads. Here we are seeing the 5 models. For first 2 models, we use the images. So I'm just uploading an image. For detecting the instruments. This is how the instruments are detected. And for segmentation also, we use the same image format. Now you can clearly see the input image and the segmentation. So for the detecting actions and the phase step, we use videos. So I'm uploading a video. These are the actions detected in the video. So for the phase step analysis also, we are using the same video format. You can clearly see the phase and the step detected. And in the combined model, we see all the 4 models combined. So yeah, we could see the complete surgical AI analysis. This is the input video and this is the annotated output. You can clearly see the phase, step, and the actions and the instruments detected. So this is the current phase and the current step. These are the atomic actions detected, grasp and history section where all the histories are being saved and user can come back and watch them anytime required. See, these are the things that we have uploaded just now. So this is our project. That's it. Thank you so much.